Recording started.
Okay, so we've just started the recording again. Thanks for coming today. This is the Manhattan GMAT Study Hall for February 17th. We're going to talk about probability, and we are going to try to emphasize those aspects of probability that are not treated in the 9-session course. Okay, again, as usual, we've got to go ahead and start with the usual warnings about what to submit and what not to submit. So here are those. You don't want to submit problems that are too general. A lot of people try to submit entire areas of the test, like geometry. Too much stuff for one study hall. Also, some people ask questions that are literally the entire test at once, like how do I solve problems faster? That's pretty much everything that we do here. By the same token, you don't want to submit problems that are too specific. So this is the big issue that a lot of people have when they submit problems. A lot of people submit things that are like basically single problems with no connection to anything else. If you submit something like that, we're just going to tell you to put it on the forum. So if you have an extraordinarily specific question that does not have any sort of general takeaway, please just go post it on the forum. This is the web address of the forums. That's what those forums are there for. Also, personal issues. Remember, this is a study hall that is watched by several hundred people. So don't submit personal issues here, personal study plans. Here's my scores. Here's the schools I want to go to. This is not the place for that. So that's, again, on the forums, we have 2 folders in which you would post questions like that. The first one is the so-called general folder. That's basically for study plans and things like that. The second is the Ask an Admissions Consultant folder if you have a question about admissions. So there you go. Also, another big deal that people are forgetting a lot of the time, you are not allowed to submit problems from the official guide. No OG problems. This has been decreasing lately, which is a good thing, that people are still submitting problems from the official guide. We're not allowed to use them for copyright-related reasons. Please do not submit problems from the official guide. Thanks. Also, the same sources that are banned on the forum are also banned here. So for the list of sources that you are not allowed to submit here, check out the forums. The first post in each folder should have a list of banned sources. The topics we do want to see, we want to see intermediate depth, not too general, not too specific. So not a single question, but not a whole class of questions either. This was one that we used as a submission. Probability, for example, today's topic is a tight enough topic that it's a legitimate suggestion, and so on. So if you do submit specific problems, please generalize the question to some extent, because otherwise it's better as a forum topic. Smiley face, if you guys understand these guidelines, any questions, type them in the text box. Otherwise, we'll move on. Smiley face if you guys understand this stuff. Okay. Also, please check the archives. There are about 30 sessions by now. We've been doing these for a while. So a lot of the topics that people are submitting have already been covered. For example, someone asked about find the assumption questions in the last couple of weeks. We did find the assumptions in March 4th edition. Somebody asked about the AWAs. We did a whole session on the AWAs a couple of months ago. A lot of stuff that people are asking about, we have already done in previous sessions, and all of the previous sessions are online as recordings. So please check the archive, scroll down on the same page where you would sign up. Please check the archive before you post questions. Okay, let's talk about probability from the standpoint of an actual definition. Text box, who knows what the actual definition of probability is? The most basic possible computational definition, not a theoretical definition. So go ahead and type that in there. Okay, yeah, what you guys are typing in the text box is pretty much correct. So the basic, a couple of you are giving me, conceptual definitions, like the chance that something happens. The problem with that is that that's not a definition. Like, not to get too much into theory and stuff, but definitions have to be in terms of things that are well-defined concepts. And the problem with chance is that chance is not a well-defined concept. Like, that's not a word that has a meaning in mathematics. So the definition of probability, basic definition of probability, is it's a fraction of the number of desired or successful outcomes over the total number of outcomes that are possible. So that's the definition. Now, so for instance, if you think about the most basic possible situations of probability, it's basically just counting stuff. For example, you were probably first introduced by rolling a die, one of the first examples of probability you may have seen. There's 6 possibilities, namely 1, 2, 3, 4, 5, and 6. So the chance, the probability of rolling an odd number, for instance, would be 3 out of 6, because there are 3 odds out of 6 possibilities. Now, there's a restriction on this. There's a condition under which this works, and if that condition is not true, then this doesn't work. Does anybody know what has to be true about the outcomes for this definition to work? Yeah, the outcomes have to be equally likely. They do also have to be mutually exclusive. That's true. Although when we say different outcomes, it's usually understood to be mutually exclusive. So the outcomes have to be equally likely. So here's a very obvious example of why this won't work if your outcomes are not equally likely. For example, let's say that you, in the text box, if you've got an issue with the whiteboard, then I'm not sure. I think that's on your end. You may want to try refreshing it or minimizing and maximizing or something. But unfortunately, I have no clue how to fix tech issues in this program. If you think about an example of playing the lottery, if you think about it, you could say there are 2 outcomes. You either win or you don't win. Therefore, the probability of winning would be 1/2. I mean, that would be really nice, but of course it's not true. The chance of winning the lottery is not actually 1/2. So again, the problem with this is what? Like, why doesn't this work? Text box. Why is the probability of winning the lottery not 1/2? One person is saying the probability that you win or don't win is 1/2. That's definitely not true. I mean, I would be going out and buying lottery tickets right now if there was a 1/2 chance of winning. Back up to our definition here. A couple of you gave me what we're looking for up here from a theory standpoint, but you're not applying it. It's because the outcomes are not equally likely. So the problem with this is that there are a lot more ways to not win the lottery than there are to win it. So it doesn't, well, okay, the way American lotteries work, it actually doesn't depend on people, because they pick balls out of a little machine and you have to get the numbers right. But these are not equally likely, which is the point. There's usually only one way to win. You have to pick all of the 6 balls correctly, but there are lots of ways to not win the lottery. So there are a lot more possible outcomes than just 2. So this analysis doesn't work because the outcomes are not equally likely. Stated outcomes are not equally likely. So for a more down-to-earth problem with this, an illustration of why it's important to phrase outcomes in ways that are equally likely, let's look at flipping a fair coin 3 times. What's the chance of getting exactly 1 head? So let's do this by just listing outcomes and counting them. Let's do this according to this basic definition of probability. And I'm going to show you one incorrect analysis of this and one correct analysis of this. An incorrect analysis would be to list the outcomes as 0 heads, 1 head, 2 heads, and 3 heads. And therefore to say that the probability is 1 out of 4. This has the same problem that does, only it's not as dramatic. I mean, it should be very obvious that winning the lottery is much more likely, or is much less likely than not winning the lottery. But again, the problem here is that these are not equally likely outcomes. It's more likely that you will get 1 head or 2 heads than that you will get 0 or 3. So what you have to do to make this correct is you have to list the outcomes in a way such that each outcome is equally likely. Does anybody know how to do that? How would you list the outcomes of 3 coin tosses in a way that they're all equally likely? Yeah, a couple of you are doing this in the text box. You have to list them as combinations of different flips. So head, 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 and so on. So, and that's the problem. And you see why these outcomes over here are not equally likely. Because 0 heads, there's only one way to get that. You have to get tail, tail, tail. But 1 head you can get in 3 different ways. You can get 1 head as head, tail, tail. You can get it as tail, head, tail, or you can get it as tail, tail, head. Same thing with 2 heads you can get in multiple different ways. You can get that in 3 different ways. You can get a head, head, tail, head, tail, head, and tail, head, head. But 3 heads you can only get in one way. You can only get that in the way that's head, head, head. So these don't work because they're not equally likely. Whereas the ones in the list on the right-hand side are equally likely. You know, like each one of these outcomes has exactly the same likelihood as all of the other ones. So these are equally likely outcomes. And so you can count them to make probability. You've got a total of 8 outcomes, of which 3 are the ones that you want. The chances of getting 1 head, that's these 3, out of 8 total possibilities. So the correct probability is 3 out of 8. Okay, any questions about these analyses, please type in the text box, smiley face if this makes sense, and then we'll try a problem. Okay, I think one person's typing a question, most of you. Let's see a couple more smileys. Smiley face if you guys understand this and can move on. Okay, that's more smileys. Good stuff. Yeah, I tell people typing questions. I'll wait a second and see what kinds of questions. Yeah, okay, one person saying this process can be very lengthy if we have more than 3 coins tossed. That's true, and for that reason, the GMAT will not probably have you toss more than 3 coins. Because one thing the GMAT will not do is, the GMAT will not make you do busy work. So they will make sure that their problem is accessible in a number of different ways. Like they're not going to make you do this with 7 coins because, yeah, it'll be a lot of work to list those things. The question about 1 versus exactly 1, if you're given a number like this, this number is not a lie. Like if it says 1 head, this means exactly 1 head. It doesn't mean at least 1 because they would have to say at least 1. What's good about that so in other words, if they give you a number that doesn't say at least, then it's an exact number. The good thing about that is that it accords with common sense. For example, if someone tells you, I have 3 kids, that means they have exactly 3 kids. It doesn't mean they might have 4 or 5. This is the same sort of thing. So when you see a number, you interpret that as exactly that number. All right, here's the problem. Before we do the problem, let me tell you how this works. If you are a veteran of these study halls, you're going to know this, but in case anybody here is new, when we do problems together, what you will see, and you're going to see it starting right now, is you're going to see these things on the board, these different buttons that you can use. Here are those. Here's what they look like. You'll see this graphic. Oops, that is not the right graphic. Okay, you'll see this. When you see this in the corner of the screen, you'll see this over there. Please use these buttons to indicate your answer. Please do not indicate your answer in the text box. Please use these to give the answer to the problem. Please use these buttons to indicate your answer. Okay, smiley face if everybody sees those buttons, if they have those available. Smiley face if you see those. Okay, good. So here's the first problem. I will put a stopwatch on the screen. Go for it. Apparently people are finding this one hard, but please try to indicate an answer in the next 20 seconds or so. Remember, this is the GMAT. The GMAT is a test on which you do have to answer everything. So even if you are guessing, please indicate some sort of guess. Thank you. Okay, so I'm going to put your statistics on the screen. Here they are. So people mostly gave answers of B and D here, but let's check this out. Long story short, there's not really going to be any short way to calculate this probability. Like, you're not going to be able to do this with standard methods of calculation because there's no patterns to primes. Like, prime numbers don't have reliable patterns. So the only way you're going to really be able to do this is you're going to have to list and count. So two-digit integers whose digits are both prime numbers. Okay, also this is probably being misinterpreted by some people, especially if you're giving an answer of E. Like if you gave a probability of 0, then you're probably not reading the question the right way. Two-digit integers whose digits are both prime. Remember that digits are considered as one-digit numbers. It doesn't matter where they are in the original number. So it means your two-digit number looks like this, where it's composed of two numbers that individually are prime. It doesn't mean that your number is prime. It means that your digits are prime. So this digit is prime, and this digit is also prime. It does not mean that your overall number is prime. So in the text box, which digits can be prime? Remember, digits are one-digit numbers. Yeah, 2, 3, 5, and 7 are prime digits. Notice that 1 is not a prime number. The only prime digits available are 2, 3, 5, and 7. So, not 1, and not 0. So what you're going to have to do is make a list of these. So in the 20s, you've got 22, 23, 25, and 27. In the 30s, you've got 32, 33, 35, and 37. In the 50s, you've got the same ones. And in the 70s, you've got the same ones. And then you just have to see which ones of these are divisible by 3. I mean, yeah, it sucks, but there are problems like this that exist where you just have to grind it, where you just have to list and count and, you know, not have much fun, but solve the problem. So if you count the ones that are, it does say the number is chosen at random, so we do know these numbers are equally likely. That's an important consideration. We want to make sure it's actually equally likely that we'll get each number. So that's what that means. So any of those numbers is an equally likely choice. The ones that are divisible by 3 are 27, 33, 72, 75, and 57. So that's exactly 5 out of 16. So this one's going to be D like dog. So list and count. I mean, there are lots of situations where you might have to find probability by just grinding out a list. Very, very doable. Any questions about this problem, please type them in the text box. Otherwise, we will move on to something new and different. Okay, doesn't look like people have questions. So let's move on. Talk about how to combine probabilities with each other. So this is a topic that is currently not covered in the 9-session course. So even if you've taken our course, this is going to be an extra topic for you. Combining probabilities of events that are mutually exclusive. Who knows how to do that? Please go ahead and type it in the text box. Disjoint is another word for the same idea. First of all, let's back up for a second. Let's make sure that you understand what mutually exclusive means. Someone give me a definition of mutually exclusive. Text box, please. What does mutually exclusive mean? Yeah, nothing is common. Both events cannot happen at the same time. It doesn't mean equally likely. It means, yeah, mutually exclusive or disjoint means no overlap. It means you can't, i.e. you can't have them happen at the same time. If one happens, the other doesn't. So how do you combine probabilities of events that are mutually exclusive? Yeah, you just add them together. It doesn't have to be sum of one. Okay, like all right, let's say here's two events that are mutually exclusive. Let's say I select a person from the phone book. Let's say the probability that the person's name starts with S is 15%. And let's say the probability that the person's name starts with Q is, let's say something like Q is 1%. So depends on how you're combining these. If it's an and situation or if it's an or situation. If it's an and situation, it's pretty easy to see that this is 0. They can't both happen. But if you want the probability that the person's name starts with S or Q, then that's going to be, you just add them together. So that's 0.16, 16%. So if two events are mutually exclusive, the takeaway here is if, yeah, the intersection of those is 0. They can't both happen. But they're not really going to ask you that. They're not going to ask you for the probability of someone's name starting with Q and starting with S, because common sense is just going to be like, that's 0. So if event 1 and event 2 are mutually exclusive, also known as disjoint, then the probability of either one of them happening, the probability of event 1 or event 2, is just the sum of the probabilities. You just add them. Okay. So there. Let's see. Samar question in the text box, the answer is yes, but there's no reason to do that. Because if they're mutually exclusive, then the probability of S and not Q is the same thing as just S. Because there's no overlap. I mean, you don't need to take an approach like that unless there's an overlap. So, and if there is an overlap, then that falls under a different class of question in our books anyway. If there is an overlap, you can think of it as an overlapping sets problem with the grid instead of a probability. Okay, separate or sequential events. Let's talk about these. Let me give you an example. So the example is this. Let's say the probability of rain tomorrow is 40%. The probability that my alarm won't go off tomorrow is let's say it's a really bad alarm, let's say it's 30%. So clearly these have nothing to do with each other. There's no influence that these have on the other. So the question is, what's the probability that it will rain and my alarm won't go off? So yeah, text box, a couple of you are giving this to me already. It's just 0.3 times 0.4. So if you want the probability that two separate or sequential events both happen, then you can multiply the probabilities. So there you go. Question in the text box, and is always less than or. Less than or equal to. It's only equal if one of them is 100%. But yes, I mean the probability that two things will both happen. If you think about this from a common sense kind of angle, then it should be pretty obvious that that's true. Like the chance that both of these things happen is going to be lower than the chance that either one does, because they both have to happen. There's a smaller chance of that happening. So yeah, unless you consider extreme cases like 0 probability or 100% probability. But yeah, if you have normal probabilities that are not 0 and are not 1, then the probability of both is lower than the probability of either. Okay, so basically the two biggest rules that you need for combining probabilities are these. If you have mutually exclusive events, then and is not interesting. If you have mutually exclusive events, then and is just 0. But or, you just add them. And then the question in the text box, no, it's the situation. Like the probability of these happening both together is nothing. It's 0. I mean, you shouldn't have to memorize a rule for that. Like if clearly your name cannot start with both S and Q. Which is, in fact, that's what it means when we say these are mutually exclusive. They can't both happen. So if you have this kind of situation, then the probability of this and this would be nothing. It would be 0. That's why we're not talking about the and situation here. The or situation here, in this case, the or situation would be it would become an overlapping set probably. The or situation can be handled with our overlapping set grid. So you don't, in other words, you don't even need to necessarily treat that as a probability question. Start and end is sort of a complicated issue because then you get into the whole idea of whether certain ethnic names are more likely to start and end with certain letters, and it's not an easy thing to answer. Because you can't reasonably treat those as separate events. Like, for example, if you look at names that start with Q, a lot of them are going to be Chinese names, and Chinese names don't end with letters like S or Z, for instance. So certain combinations are going to be more likely than others, so that you just won't be able to talk about. They're not separate events. Okay, but does everybody at least get these two basic principles? If you have separate events and you want the probability that both of them will happen, you multiply. If you have mutually exclusive events and you want the probability that either one of them happens, then you add. Smiley face if these things make sense, and we'll look at a problem. Smiley face if this makes sense. Okay, looking for a few more smileys here. About half of you guys. Okay. All right, good stuff. Let's take a look. Separate, both happen, then you multiply. Okay, here's a slide. Let's talk about these. These are not multiple choice questions. And then let me actually add one more question to the mix. I'll do that later. All right, let's talk about this. A standard deck of cards. You got 52 cards. Half of them are black and half of them are red. So 26 black cards, 26 red cards. If you take 2 cards from a deck without replacement, meaning you take 2 different cards. What is the probability that both of the cards are black? Text box, please. How do you do that? What replacement means is, I mean, replacement is exactly what it sounds like it means, but what it means is that with replacement would mean you could get the same card twice. Like that would mean you pick a card and then you put it back, that's the replacement part, and then you pick another card. So without replacement means you take 2 different cards out of the deck. That's going to matter because, let's talk about this. These are separate events. The first card and the second card are separate. So we want the first card black and we want the second card also black. So first card black, second card black. The probability that the first card is black is 26 out of 52, which is 1/2. So that much is probably pretty straightforward. But remember that there's no replacement. You don't put this card back. So how many cards are left in the deck at this point? There's only 51 cards left in the deck. So, and then you have if you're still examining this, it means you took a black card. So now there's only 25 cards left in the deck. And 25 black cards out of 51. It's not out of 52 anymore because you don't put the card back. So notice that the probabilities will change as you take out more cards because you're not putting them back. So this simplifies to 1/2 over here on the left. So that's 1/2. So you wind up with 25 out of 102. Any questions about that? Text box if you have questions about that. Okay, well, there's a few people typing, so we'll wait and see what they type. So who's got an answer to that one? Why not add? Yeah, I mean, okay. The reason that you should know in terms of theory is what these guys are saying. It's a situation with 2 separate events that you want them both to happen. It's an and situation. So you want the first card to be black and you want the second card to be black. So it's not an or situation, and these are not mutually exclusive. I mean, it's perfectly possible for both of these to work. But it's an and situation with sequential events. But also make sure you think about this. Make sure you try to develop a sort of common sense, intuition, understanding of probability. Probability is the chance that something will happen. And what should be clear is that the chance that both cards are black is definitely lower than just the chance the first card is black. Like, if you added these probabilities together, that wouldn't make sense because you'd be saying that it would be more likely to have both of them black than just to have the first one black. That would be a non-reasonable answer. So make sure you develop it from both angles. Like, make sure you develop it from the angle of what kinds of numbers are reasonable on these things, but also make sure you know these 2 rules, the and rule and the or. Okay, let's see what are these guys saying. If it is without, well, with replacement would be the same, only this would just be 26 again, and this would be 52 again. If you put the card back, then probability would be the same. Okay. Other questions? Some people are still typing things. Okay, I still see 2 people typing. Let's move on to the second question. What is the probability that 2 red cards are selected? It's the same. So it's the same situation that we have with the first one. Except instead of black, it's red. So, because there's the same number of reds as there are blacks in the deck, so this is not going to work out any differently. The probability the first card is red is still 26 out of 52. And then once you've taken a red card out of the deck, then there's 25 red cards left out of the 51 cards that are still in the deck. So there you go. Okay, it looks like some people are typing stuff. No, this is separate. This is not a continuation. This is just from. These are all possibilities from this first selection of 2 cards. So this is a separate problem from this. Here, replacement could be possible. No. Like this prompt goes with all 3 of these problems. Like this, if 2 cards are taken from a deck without replacement, applies to all of this. This is without replacement. This is a separate problem that is also without replacement. And I don't know why that happened. This is a separate problem that's also without replacement, and this is a third problem that is also. All 3 of these problems go with the same prompt. Okay, other questions about, some of you guys have text in your text box. One thing about this program, by the way, if you have any letters in your text box, then it'll look like you're typing. So if you have letters in your text box and you are not typing, please erase them, because otherwise I'll be waiting for you and you're not actually typing anything. So, okay, let's look at this one. What's the probability that 1 black card and 1 red card are selected? Well, let's do this in 2 ways. Do that in 2 ways. The first way we can do this is to realize that if we take these 3 options, among these 3 options, we've got all possibilities. Like, the only ways that 2 draws from a deck can turn out are these 3 ways. You can either get 2 blacks, you get 2 reds, or get 1 black and 1 red. Okay, smiley face if that makes sense, that those are all 3 possibilities. Like, these are the only possibilities. So does anybody know what that means? I spelled these wrong. Let me fix that. Does anybody know what that means in terms of probability? Like, if you have every possible event, then what should be true regarding probabilities? Does anybody know where we're going with that? Yeah, the sum is 1. So the first way of doing this is just use the fact that the sum of all possible probabilities is 1. So if you do that, this probability is 1 minus the probability of everything else. That's a useful takeaway. If you can find the probabilities of the other events, then your probability is just 1 minus the probability of those events. So that's 1 minus, the other events together are 25 over 102 plus 25 over 102. So those together are 50 out of 102. So if you do that, then you get 102 minus 50. So that's 52 out of 102, which reduces to 26 out of 51. So this needs to be the answer because that's how probability works. Like you've got, these 3 outcomes are literally everything that can happen. So if our probabilities don't add up to 1, then something is wrong with our analysis. So about half the people got 13 out of 51, the other half got 26 out of 51. But this is the right answer because it has to be. So smiley face, if you guys understand this work over here. Even if you're not sure how to do it the other way yet, smiley face, if this work on this side makes sense. It's 1 minus probability of everything else. Okay, now let's do it by multiplication. Here's the deal. If you use multiplication, the order matters, and it turns out when you multiply probabilities, the order always matters. Always, always. When you multiply probabilities of consecutive choices, the order has to be taken into account. So the reason these calculations worked upstairs is because there's only one order you can do this in. I mean, the only way to get 2 black cards is to get a black one and then get another black one. It's the only way to do it. Similarly, the only way this can happen is if you get a red card and then you get another red card. It's the only way it can work. On the other hand, the issue is that this can happen in 2 ways. It can happen as red, then black, or it can happen as black, then red. And so you need to calculate these probabilities separately. So the probability of getting red, then black, red, you've got 26 out of 52. If you pick that, there are 26 blacks still left because you took a red. So out of those 51 remaining cards, there's 26 black ones. And that's multiplication. And then this probability is the same, 26 blacks out of 52. And then if you took a black, then that means there's 26 reds still hanging around out of those 51. And then notice these are mutually exclusive. So you want either one of these to happen. So the overall situation here is an OR situation. You either want red then black or black then red. These are definitely mutually exclusive because you can't do it in both of these ways at the same time. So if you reduce these fractions, then you wind up with 26 over 102 plus 26 over 102, which is 52 over 102, which is 26 over 51, which is what we want. So same answer we get either way. So the important takeaway that you want to get out of this is that when you use multiplication on probabilities, you have to take into account the different orders in which stuff can happen. So there you go. In general, there are, okay, the question in the text box is there a pattern? there are patterns, yes, of course there are patterns, but for the GMAT, there are not really patterns that are terribly worth memorizing, because like the chance that you're going to see the same kind of pattern over and over again is very low. It's better to think about each problem individually and just think about the orders that are possible in that problem. Because, okay, if this were a statistics class, you get these problems where it's like, what's the chance that you pick 7 red cards out of your 12 cards? That you need to memorize some formulas for, but the GMAT's not going to do that. Because the whole goal of the GMAT is to be a test where people who just memorize lots of formulas do not have any sort of advantage. And so remember, the GMAT is purposely structured in ways that just memorizing formulas will not help you very much. So keep that in mind. Let's try, I don't see anybody else typing anything, so let's try problem. Let's try this one first. Okay, here's you got your A through E options. Remember to please use the A through E options. Please use these options. Please use those buttons, these buttons right here. Here's your stopwatch. I'll give you a little bit less time because this problem's not as long as the others. Go for it. Okay, that's about 2 minutes total, including the time I spent talking. So let's wrap up, and please pick an answer even if you have to guess. So we're waiting on Amelia and Shani and Sahana. Okay. Everyone except Shani and Sahana. And then someone just undid their answer. Okay. All right, here are your statistics. We had one person who didn't answer it. So most of you have this one correct. Let's take a quick look. You're choosing it's a choice without replacement, which is, in general, you have to kind of use common sense to figure out whether there is replacement or not. Like, let me give you an example. Let me give you an example of what I mean. Like, you're not usually going to be told whether there is replacement or not. Replacement versus no replacement. Usually you won't normally be told explicitly which of these two. Like, you won't normally be told explicitly which of these is the case. What you'll have to do is you'll have to just use common sense to figure it out. Or just, your own intuition about the situation. All right, so for example, if you say you select 2 of 6 workers for a survey, you're definitely not going to select the same worker twice. So that's no replacement. Even if they don't tell you that, you're expected to figure that out. If you say something like, if you're given something like, you pick a 5-digit code in which each digit is odd. In this case, there's no restriction against picking the same digit. In this case, the default assumption is that the digits don't have to be different. So this is with replacement. And I mean, you're expected to just use your own intuition about the situation at hand to figure out whether there is replacement or not. So in this kind of situation, we're choosing two people. So this is a no replacement situation because you can't pick the same person twice. So i.e. no replacement. So what's cool about this problem is that a lot of you guys were probably looking for 1/30th, and they're nice enough they didn't give it to you. I mean, the most common answer that people are looking for on this problem is 1 out of 30, if they get it wrong. But they don't give you that. So remember, these are sequential choices without replacement. So you multiply. You want Joshua and Jose. It's an and situation. So multiply. We got to consider order. Remember, order matters. So we need both possible orders. The possible orders are Joshua, then Jose, and then the other possible order is Jose and then Josh. Okay. Abhishek, the short answer to that question is we don't care. I'll talk more about that later. But when you are studying this stuff, you shouldn't. The only people who should care about difficulty levels are people who are scoring like mid-500s and lower, so that they can avoid problems that are just out of their league. Other times you just shouldn't care. We'll talk more about that later. Okay, probability of Joshua then Jose, the probability of picking Josh, there are 6 people, so the probability of getting Josh first is 1 out of 6. And then the probability of getting Jose after that is 1 out of 5. And then Jose first, it would be 1 out of 6, and Josh would be 1 out of 5. So then these two cases are mutually exclusive to each other. So we will take these and we add them together. Because the overall structure of this, once you've figured out these two possibilities, the overall construction of the problem is an or situation. It's either Josh then Jose or Jose then Josh. So it's this or this. So you add those together and you get 1/15, which is A. Okay. Questions about this work right here? Yeah, another way that you can do this is, I definitely don't want this session to devolve into a session about combinatorics, but another way that you can do this problem is, yeah, okay, let's do two more ways to do it. To R. Somerville, yes, excellent. One other approach is to just say that you get first choice Josh or Jose. And then once you've got Josh or Jose, then you got to pick the other one. So yeah, you can do a combined approach. This is more intuitive. So people who struggle, people who don't have a common sense grasp of probability probably won't like this kind of solution very much. Like if your approach to probability is to memorize stuff, this is going to be very difficult. But if you understand this from an intuitive kind of standpoint, then this is a good approach. So you got to kind of know yourself here. If you're learning this stuff mostly by memorizing rules, this approach will be harder. But if you're learning mostly by understanding it intuitively, then yes. So the probability of picking either Josh or Jose is 2 out of 6. But once you've got one of those guys, then you just have to pick whoever is the other one, which is one person remaining out of the 5 people that are left. You can also just do it this way. So that's an intuitive shortcut that's doable. Again, if your approach is memorizing rules, this one's going to be a tough one. The other way you can do it is not, I don't even want to say the other way. Another way that you can do this problem is to just use the old list and count method. The basic definition of probability is number of successful outcomes out of number of total outcomes. So this, the number of, so in this case, an outcome is a choice of 2 people out of the 6. So there's only one successful outcome. Namely, you pick Joshua and Jose. On the other hand, the total number of outcomes is the total number of groups of 2 that can be selected. So if you know how to use combinatorics to do this, then you'll just get a number. Again, this is not a combinatorics unit, so I don't want to discuss that today. But if you use combinatorics, you can calculate 15. If you don't know combinatorial techniques, you could just make a list. It doesn't really take very long. If you're uncomfortable with the combinatorics, then make a list. Let's say Joshua and Jose are people 1 and 2. So then you can have 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. You can have 2 and 3, 2 and 4, 2 and 5, 2 and 6. Wow, eliminated weird with numbers. Okay, you can have 2 and 3, 2 and 4, 2 and 5, 2 and 6. Joshua and Jose are people 1 and 2 here. Here's all your different groups that you can have. 15 different groups. So out of these 15 groups, only one of them is actually Joshua and Jose. So that's the very first one. So 1 out of 15. That's the other way to go. Okay. So there we go. When you do this, you don't have to think about order because you're not multiplying probabilities. If you do think about order, you can also do it that way. I mean, when you think about groups of 2 people, you don't have to think about the order, which is the point. Like, remember what we said. If you do need orders when you are multiplying probabilities together, but in this situation, we are not multiplying probabilities together. So we don't have to do that. I mean, if you do consider the choices as ordered, you can also do the problem that way. I mean, it'll take you twice as long, but you can also make an ordered list, although it's not necessary here. If you make an ordered list, then you just get twice as many. You're just going to get each group 2 times. You're just going to have this, 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 then you're going to have 2 everybody else. I mean, you don't need to make an order list here because you're not multiplying probabilities. But if you do, you'll still get the problem right. It'll just take it longer. And then that's why it's important for you to really understand. Like, a lot of people just memorize what they think are rules, but they don't memorize the context in which those rules apply. I mean, you can't do that. Like, you can't just say I have to take order into account, period, because it's not true. You have to say I have to take order into account when I am doing what. And in that case, it's when I'm multiplying probabilities together. So in this case, I'm not doing that, so that rule doesn't apply here. It's like applying soccer rules to a hockey game. So here's my 30 cases. In these, now there are 30 cases instead of 15. This is still doable in 2 minutes without much of an issue. But now I have 2 groups that are Joshua and Jose, and so now it's 2 out of 30. So it's still 115. But remember that when you learn rules like this, you need to know when you are doing what. So remember, the statement of the rule was explicitly when you multiply probabilities, you always have to take into account order. Like, if you've studied combinatorics, you know there is a whole group of combinatorics things that don't use order. So it's definitely possible to have non-ordered situations, just not when you multiply probabilities. That's all. Okay. Yes, you could, but that would be a very not efficient way to do it. I mean, you would wind up doing a lot more work than you would have to do in that case. But yes, you theoretically could. Okay, let's move on. We're probably a little bit sick of doing that problem. So let's try this one. This one's probably a little bit more challenging. A 3-digit positive integer is chosen at random from all 3-digit positive integers. By the way, a 3-digit positive integer, the first digit is not 0. So make sure you understand that. 3-digit integers are from 100 through 999. Like 086 would not count as a 3-digit integer. That would be a 2-digit integer. Also, make sure you know that 0 is even. If you don't know this, now you know this. But I'm just going to tell you this just so you don't miss the problem for that reason. So what is the probability that the product of its digits is even? Go for it. Guess pretty soon here. Notice that this is not the kind of problem where you can really list things because there would be 900 things to list. So unfortunately, we got to solve this one with theory. But please pick an answer in the next like 10 or 15 seconds. Thank you. Okay, we've got votes from everyone. Here are your results. Let's take a look. I mean, this problem is not what I would call super easy, but it's useful. It's good preparation. Because it also touches on some number property considerations, too. It's a little bit less one-sided than the problems you've been seeing so far. So let's take a look. Did you guys, a lot of you probably had to guess. Okay, you don't have to type on here or whatever if you had to guess. But let's talk about if you just don't know how to do this. At least we know that the probability is something out of what number? Like what's the denominator of this? We'll see if you guys can figure out where we're going with this. Yeah, it's out of 900. So, I mean, as weird as that is, that's enough to eliminate two choices. Because 54 doesn't go into 900, and neither does 8. So these can't reduce, like 54 and 8 don't go into 900. So C and D would be impossible to get from this expression. So you can at least eliminate C and D, even if you have no clue how to solve this problem, if you just know that there are 900 numbers in this list. Because this is not anything out of 900, and neither is this. Like this fraction would have to reduce to the correct answer. So that's an interesting elimination. It's worth thinking about in the future. Because remember, probabilities are, like every probability at the end of the day is this kind of fraction. So, except for continuous probabilities, they don't test us. So every probability on this test will be a fraction like this, and so you might be able to make eliminations based on that. All right, now let's do this for real. Let's talk about the problem on the next page. Or not. Okay, I'm just going to go ahead and delete that, and then we'll stay on this page. Okay. How do you get an even product? Yeah, see, there's some misunderstandings here. A couple people are saying all even. That's not necessary. And if that were necessary, you would have a much smaller probability than this, because the chance that all 3 digits are even is pretty small. The way that you get an even product is if any digit at all is even. And remember your number properties, if you multiply an even number times absolutely anything, you get an even number. So the problem is there are lots of different ways to do this. You can have 3 evens, you can have 2 evens and an odd, which you can do in 3 different ways. Or you can have 2 odds and an even, which you can also do in 3 different ways. This is a lot of work. On the other hand, remember what we said about shortcuts. If you can find the probability of all the events you don't want, then you can just subtract that from 1. So what are the ones that I don't want? Yeah, the numbers I don't want have odd products. There's only one way to do that, which is odd, odd, odd. So all I got to do is find 1 minus the probability of all odd. So it's going to be 1 minus. So, and you got to be real careful here. So there's 2 ways to do this. Let's do this both ways. If you want to do this by multiplying probabilities, you can, because now it's an AND situation. So this is the first digit odd, and second digit odd, and third digit odd. So we can do it by multiplying probabilities. Now be very careful here. What is the probability that the first digit is odd? Be careful. Text box, please. And be careful, it's not a half. No, it isn't. So far, all three answers in the text box are incorrect. It's not a half, it's not 1/5, it's not 4/9. It's also not 4/10. Yeah, it's 5 out of 9. Because notice you can't pick 0 for the first digit. So the only digits that you're allowed to pick for the first digit are 1 through 9, not 0 through 9. So because this digit is not allowed to be 0, you're only picking out of 9 digits, not 10. So this is 5 out of 9. The other digits have no such restriction, so this really is 5 out of 10. And so is this. But that first problem, you got to be real careful with that first one, because the first digit is not allowed to be 0. So that's 1 minus, you can cancel both of those and make 1/2 out of them. So these will be 1/2 each. So let's write those out, 1/2. The reason why these are 5 out of 9 is because you have, the first one is 5 out of 9 because you have 9 different choices of digit, which are 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 5 of those are successes. 5 odd digits out of 9 total digits. The other two ones, you have 10 digits to pick out of, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and of those 5 are still odd. So smiley face, if you were one of the question askers, smiley face if that makes sense to you. Okay, good. All right, so that's 1 minus 5 out of, once you reduce those fractions down, you get 1 minus 5 out of 36. So that's 31 out of 36. The other way you can do this is instead of multiplying probabilities, you can just do 1 minus the total number of odd odds over the total number of numbers. So, or you can do 1 minus, you just, it's like a literal regular probability fraction where you just count stuff. So the total number of odd is total number of odd is going to be 5 times 5 times 5, because that's the number of odd digits you have, 5 times 5 times 5, over the total number of choices altogether, which is 100 through 999, so that's 900 numbers. So out of 900 total numbers, you've got 125. I mean, this one's more math that you've got to do. You have to spend more time on stuff like reducing fractions, but ultimately at the end of the day, you get the same answer. So 31 out of 36. Well, 1/2 is the answer that you get if you forget that your first digit is not allowed to be 0. Because if you count numbers like 006, then you'll think you get 1/2, but those don't count as 3-digit numbers. Okay, questions, please. Anybody have any questions? Okay, if not, we may be able to squeeze one more problem in here. Let's see. Okay. All right, let's see if we can cram in. Can I explain the underlying logic, how it covers all cases? I don't really understand what that question means. It's kind of general. I mean, it almost sounds like you're asking me to explain the entire theory of evens and odds. So I'm not really following that. but maybe you can type it in there. Let's get one more question on the board. We can probably just do that real quick. All right, try this one. I'm going to clear out your answers. Again, it'll show up in just a second here. Try this one. Please use the indicated buttons. This is from GMAT Prep. All the problems today are from GMAT Prep except for the one. The last one I wrote myself. The others are all from GMAT Prep. So these, okay, here's a timer for you. Give you a little bit more time because there's a lot of words in it. So have fun. About 2.5 minutes, so if you need to make a guess, please make a guess. And then we'll have a quick discussion. Okay. Here's the story. So, overwhelming majority of correct answer here, but let's take a look. First takeaway about this, by the way, because probability is, a lot of people group probability in their head along with combinatorics. And I mean, that's understandable because probability and combinatorics are pretty close cousins. But the difference, the problem with doing that is that a lot of people think about probability in a very non-common sense way if they do that. So you got to remember, combinatorics is not really intuitive at all, but probability totally is. And probability is something, unlike combinatorics, probability is often very intuitive, i.e. you can think about it in a very real world sort of way and eliminate answers that don't make reasonable sense. For instance, Leo is flipping through 3 different stations, and if you get a song that works at any point, then you win. So, answers A and B, they don't make sense. Because the chance that you get a song you like on the first station that you flip to is already 30%. So use your if you have to guess. So if you have to guess, then use intuition to rule out answers that don't make sense. So on the other hand, and even if you're not guessing, even if you think you have an answer to the problem, you should still use intuition. And what you should use intuition for in that case is to check your answer. So if you get an answer, still use intuition to check your answer for reasonableness. So in this case, the first station, you've already got a 30% chance. So clearly the probability that you will ever hear a song you like is more than 30%, because it's already 30% the first time, plus more options the second time and third time. So these are less than 30% by a lot, and so that just doesn't, those are not reasonable. It's definitely more than 30%. Also, one thing that you should know, another thing that you should know about the GMAT, remember that GMAT problems will never just require you to add or multiply given numbers to do one simple operation on given numbers. These are trap answers. So, like, in other words, if you think the answer to this problem is just 30% plus 30% plus 30%, it's not going to be. Think again. Same thing if you, like, in other words, the answer here will definitely not be just 30% plus 30% plus 30%. No matter what the problem is, they don't write problems that do that. Also, the answer will definitely not be just 0.30 times 0.30 times 0.30. I'm going to check why, because that's 1 minus 0.3. If so, then no. Because if I had, you know, like 20 radio stations, then my chance would be pretty darn close to 100%. But these are trap answers. So E is a trap answer. A is a trap answer. Don't pick answers that look like they are super obvious. Like if you think that you can do 5 seconds of work, you're probably wrong. That's basically the deal. All right, now the way that you actually have to approach this problem is you have to consider, and we're going to run through this relatively quickly because we're into the overtime zone now. So let's get a quick treatment of this before we call it a day. There's 3 different possibilities here, and they're mutually exclusive. Here's what they are. Basically, either you can get the song on the first station, or you can get it, if it's not on the first station, but you get it on the second station. Or the last possibility is that it's not on either of the first 2 stations, but you get it on the third station. Those are mutually exclusive possibilities. So that's why you have to do it this way. You can't just do 0.3 plus 0.3 plus 0.3 because those overlap. Like you have to, it's not mutually exclusive that the songs would be on the different stations. So you can't just add 0.3 3 times. But the chance that you get it on the first station really is just 0.3. The chance that you get it not on the first station is 0.7. Then, yeah, that's what we're going to get to next. That's right. There is not a chance that Leo just turns off the radio and can't hear the song. Like you don't have to consider freakish possibilities like that. Because it says he listens to them and he turns to them. So you don't have to consider cases where you don't listen to them. 0.7, not on the first station, but yes on the second station. Because if the chance that you hear it is 30%, the chance that you don't hear it must be 70%. So this is the chance of not hearing it on the first station. It's an and situation, not hearing it on the first and yes hearing it on the second one. And then MAT, yes, that would be interesting, but that's too much busy work for the GMAT. Like the GMAT is not a busy work test. That's one thing you've got to realize. Like GMAT problems are all pretty short. They're not easy, they're not conventional, but they are not busy work. Like they would not make you do that much grind. This is 0.7 for the first station, also 0.7 for the second station, and then you get your 0.3. Yeah, we're going to get there. So this is, you can add these up. If you add these up, you get a total of 0.657. And so that would be D like dog. The other way to do this, as a number of individuals here are pointing out, is you can treat this as 1 minus the opposite event. So let's talk about that. Let's take another screen and do it on another screen. If you want to do it that way, then here's how you would do that. You could also do 1 minus possibilities that you don't want. Possibilities that you don't want. So that's 1 minus the problem. The only thing you don't want is for none of the stations to be playing it. So the probability that no station is playing the song is 0.7 for all of them, and you multiply them all together. And that's the non-desired case, so we take 1 minus that case. If you know that 7 cubed is 343, then this is quick math. So there you go. It is, yeah, it's sequential events in the smaller cases and mutually exclusive in the larger. Overall, it's large mutually exclusive situations, which within them have these like sub situations that are just multiplied together. Good resource for probability questions. You can probably search the web. I mean, I would avoid, if I were you, I would search the web, but I would avoid any problem that's too busy work-ish. But I would look for, you know, maybe basic, I mean, you could look them up as basic probability exercises. And like, because if this were in a stats course, these would be classified as basic probability problems. So, yeah, likelihood. Jenny, you're listening. You're definitely listening to the station because it tells you that. He first turns to this, then he turns to the second station, and then he turns to the third station. So it's definitive that you're listening to these stations. That's not at issue here. But yeah. Yeah, no, if not, because yeah, if you get a station, if you get a song you like, then you're done. But that's why this is just 0.3. That's why you don't have to worry about the other cases here, because if you get either of these cases, you don't bother with the third station because you're done. You got the song you like, so you don't proceed through the stations in these outcomes. So yeah. Well, all right. 0.7 is the chance that you don't hear the song you like, which means you move on to the next station, according to I mean, there's no difference, really, between those two. Like, not hearing the song you want is the same thing as moving on to the next station in this problem, because that's what he does. If he doesn't hear the song he likes, he moves on. Zip says, I've seen combination of probability and combinatorics. I mean, well, there are some problems that you can think of that way if you want to. Like, for instance, this problem you can think of as that if you want. I mean, you don't have to. Like, here's a way of doing this that doesn't involve combinatorics, where you just do this. But then here's a way of doing that problem that does involve combinatorics. So in most of those cases, it's probably going to be doable like one way with combinatorics and another way without it. So that's kind of the nature of probability question. Okay, let's try to wrap up here pretty soon. Let's see. There's any super last minute questions about this stuff. The next session is whatever 2 weeks from now is. So I'm not a super calendar jockey. I have no idea what date that would be, but it's whatever is 2 days from today. 2 weeks from today. So, all right, I'm going to kill the recording. If you have any administrative questions, feel free to ask. Otherwise, yeah, have a good 2 weeks.